Welcome to the section on training and optimization. The authors of the paper pre-trained convolutional layers on the ImageNet 1000 class competition dataset. Now we are gonna, instead of pre-training, that's instead of trying to pre-train this, we are gonna use a mobile net which has already been pre-trained. Now for pre-training we use the first 20 convolutional layers, so we shall not repeat this exactly because this is going to take long, and also because we're trying to come up with a model which can be used in low resource environments. So this is for over a week and achieve this top 5 accuracy of 88% on the ImageNet 2012 validation set, which is comparable to the Google Net models in Cafe's model zoo. Then after that, they add convolution and connected layers to the pre-trained networks. So according to Ren et al., this was going to increase performance. Now following the example, we add 4 convolutional layers and 2 fully connected layers with randomly initialized weights. Detection often requires fine-grained visual information, so we increase the input resolution of the network from 224 by 224 to 448 by 448. That's, we train at this and then we detect at this. Now our final layer predicts both class probabilities and bounding box coordinates. We normalize the bounding box coordinate width and height by the image width and height so that they fall between 0 and 1. We've seen this already. We parameterize the bounding box x and y to be offsets of a particular grid cell location, so they are also bound between 0 and 1. So we saw this already. We use a linear activation function for the final layer, and all other layers use the following leaky rectified linear activation. So they use the leaky ReLU instead of the ReLU for all other layers. And then they optimize using the following loss. Now also, they trained the network for about 135 epochs on the training and validation data from this Pascal VOC 2007 and 2012 data sets. When testing, we also include this. Throughout the training, they use a batch size of 64 and a momentum of 0.9 and decay of 0.005. Learning rate scheduling is as follows. For the first epochs, they raise the learning rate from 10 to the negative 3 to 10 to the negative 2. Then if we start at a higher learning rate, that's if they actually started at this, at 10 to the negative 2, the model often diverges due to unstable gradients. So it's preferable to start at 10 to the negative 3 and then increase to 10 to the negative 2 and then reduce again. So we continue training at this for 75 epochs, then decrease to 10 to the negative 3 for 30 epochs, and finally decrease again to 10 to the negative 4 for 30 epochs. So it's very important that you actually redo this training by yourself. Also, to avoid overfitting, they use dropout and extensive data augmentation. The dropout layer will rate 0.5 after the first connected layer, prevents co-adaptation between layers. For data augmentation, they introduce the random scaling and translations of up to 20% of the original image size. We also randomly adjust the exposure and saturation of the image by up to a factor of 1.5 in the HSV color space. Now we go on to compile the model right here, and then we could now train our model. So we have this YOLO version 1, which is now object detection folder. We have this callback, which monitors the loss, and we have the train generator, which we had declared previously right here. It was somewhere, yeah, so that's it. Now let's run this. Now after training for several epochs, we have the following results. We could see from here that this is not the kind of results we expect to have, so we have to debug this code. So let's stop this, we get back to this, and now we could print out the different losses we have right here. So print this out, and now we get into the eager mode. So we now put this in eager mode. Once we are in eager mode, we could run this and then have to actually get these values. So run this, yeah, and then we could get the values for the different losses as they've been trained. Now we could see clearly that the only loss which gives us negative values is the second one, which is the no object loss. So if we get back to that, we actually have that. We have this has been omitted. So let's take this from here and put it back. So we'll do that, and that's fine. So we have this. Let's run it now. Let's take this. Let's comment this now since we've had a right. Run this. Now it started from this value actually because it was already giving us very poor value. So what we could do is we could actually recompile the model or reinitialize the model. So we'll come back right here. We've stopped that. Run this again. We now recompile the model. Let's get back to graph mode. So we'll compile the model and then we run this. Now after running this, we have this error where we're told the shape must be rank 1 but it's rank 0 at the level of the reshape with input shape is this. So let's get back to the loss function and try to understand that. Now before looking at that, we could look at the error from here. So we have actually this target equals, so this is exactly where we have this error, and looking at this we see exactly where we need to solve this or how we need to solve this problem. So we'll get back to this. So instead of this, we insert creators list. So we have this. So we could also take into consideration the batch dimension. So let's have this, and that's fine. So let's run it now again, and we see that it's now training just fine. So we just keep training this model. Now our model is taking a while to train. So what we could do is to make sure our model doesn't have any bug, we'll try to overfit it. So we'll actually reduce the number of elements in the validation set. So we've reduced this. We've left from 155 elements to just 6 elements so that we could overfit it and be sure that there are no bugs anywhere. So let's rerun this again. We have this. We have this error because there's no the batch size is too large. So let's reduce the batch size. Actually, we have 6 values, so we could say a batch size of 3. Run this now again, and this is what we get. Now note that it's actually useless for you to kind of like work with the whole data set only to later on find out that there was a problem in your code. So it's preferable to actually work with fewer elements, test whether the code or whether the model overfits, like what it's doing right here, and then later on now test it on a larger data set. So after training for a while, we have this. But when we modify the lambdas and getting or putting the exact values we have from the papers, this is the value for the loss we now get. So our model has successfully overfitted, which is what we wanted. Now we could go ahead and work with the train data, so we can have that from there. Okay, so let's run this. But before that starts, let's take this off and modify the batch size. So let's take back the batch size to value of 32. Run this. We could even initialize the model again. So we have that. We have this, and then this. Well, we've been training for a while now, and these are the results we're obtaining. Now, depending on the kind of GPU resources or even TPUs you're working with, you may even train faster. But note that it's important that you actually go through this training of the 26,000 examples in our training set, as this will permit you to be able to train this on an averagely large data set like what we have here. So apart from training from the training data set we get here, you could even get more data to add to that, as training such large data sets is a skill on its own, and you have to actually master that skill. So never hesitate to train large data sets.